Welcome to the lecture series on digital electronics 18EC302C. In today's lecture, we are going to look at, we will introduce logic families, digital logic families. So, first we'll see what is meant by logic family, and next we'll go in deep into the details of the logic families, that is their classification and characteristics, and we'll look at three important logic circuits and their operation, that is their working, and next we look at a comparison of the various logic families, and next we will be introduced with some of the names of the ICs in this unit. So before looking at the detailed description of all these, first we'll see what is meant by logic family. So this is the unit which is about understanding different logic families. So before that, first we'll see what is meant by logic family and what is that which is specific to a particular logic family, that will see. So when we want to build a very large digital system, we are required to realize a number of digital logic functions. And to realize a logic function, we require a variety of devices. So to realize different types of logic functions, we require a variety of digital circuits. We can see all these circuits, or each of all these circuits, have different circuit configurations and production technologies. That means each of them will be using different semiconductor devices and circuit elements, and they will be using different interconnection between the devices and the circuit elements. Maybe they are produced by different production technologies that are used to produce the semiconductor devices. So that means a number of circuits are there, and each of those circuits have different configuration and different production technology. And these all circuits are used to realize the digital logic functions. So when they have different circuit configuration and different production technologies, those digital circuits will possess different characteristics also. So if certain type of, if one group of circuits, digital circuits, are produced by same circuit configuration or similar circuit configuration and similar production technology, they will possess similar characteristics also, and that group or family is called as a logic family. So I can say that the digital logic circuits which are from particular family will possess similar characteristics. So here characteristics means the electrical characteristics, like the voltage and current characteristics, the voltage and current requirements. So why this is important? Because when we want to form a very big digital system require a number of digital circuits, and these digital circuits must be interconnected. And if all these circuits are from same family, they will possess similar characteristics and will not have any compatible issues if they are from the same family. But if they are from the different family, the circuits may not be compatible when you want to interconnect them. So, to build a better digital system, you should have a knowledge of the logic families and the characteristics of the particular logic family of the circuits that are used to build a digital system. So, we will look at the various characteristics that are important for to understand a logic family, circuits of a logic family, and here we list the important characteristics: the input and output logic levels, namely the input and output logic levels, and supply voltage requirements, and propagation delay, and noise margin, fan in, fan out, power dissipation, the figure of light. So these are the various characteristics that we look for circuits from a particular family, and these characteristics will enable us to whether use a circuit from a particular family in that system or not. So we'll look at all these characteristics, that is what is meant by this particular characteristic and what is the use of these characteristics and how it will be useful, what is the importance of these characteristics for a circuit, for a digital logic circuit, that we will be discussing later. So before going to discuss all these characteristics in detail, we will first look at the classification of the logic families. So basically, this classification is based upon the devices used to make the logic circuits and the mode of operation of the devices in a particular circuit. So based on the two things, the type of device, semiconductor device that we are using to build the circuit, to build the logic circuit, and the mode of operation of that particular device in the circuit. So here, broadly, the logic families are classified into bipolar families and unipolar families, and this is based on the semiconductor devices that are used to make the circuits, that are used to build the circuit. If we will be using either diodes or transistors which are bipolar in nature to build the digital logic circuits, then all those circuits will come under bipolar families. But on the other hand, if we use the unipolar devices, that is field effect transistors, then those digital circuits will be part of unipolar families. And under unipolar families, depending on what is the exact device, semiconductor device that is used to build the digital circuit, it is categorized into three categories: PMOS family, NMOS family, and CMOS family. So that is when the digital circuit uses only P-type, P-channel MOSFET and belongs to PMOS family, and when the digital circuit uses N-channel MOSFET devices, it belongs to NMOS family, and when the digital circuit uses it is built by using at least one PMOS FET and N-channel MOSFET, it belongs to the family called CMOS family. Next, so this is the family called unipolar family, which is further divided to PMOS family, NMOS family and CMOS family. Next we look at bipolar family, where these the semiconductor devices used are either bipolar junction transistor or diodes. So again here this is classified further into two categories, namely saturated families and non-saturated families. So this classification of saturated and non-saturated families is based on the mode of operation of the devices. So if the devices are going into saturation, so if the devices are operating in saturation mode, they will come under saturated families, and if the devices are operating in non-saturated mode, they will come under non-saturated families. And the non-saturated families we have further classification based on the type of circuit configuration. One family is Schottky transistor logic, and the other is ECL, emitter coupled logic family. So coming to the saturated families, we have further classified saturated families into a number of other families depending on the type of circuit elements used. The first one is resistor transistor logic. So RTL, resistor transistor logic. And the next family is DCTL, direct coupled transistor logic, and diode transistor logic, DTL family. Next, high threshold logic, HTL family. Next, integrated injection logic family, IAL family, and transistor logic, TTL family. So this is the entire classification of the logic families based on the devices and their mode of operation. So each of the family has the digital circuits whose characters are similar, and they are different from the circuits of the other family. So that means when you interconnect circuits from the same family, there will not be any compatible issues, that is voltage and current requirements. But if you want to interface the circuits from one family to the circuits of other family, there may be the compatibility issues, and that will be solved by using some techniques. Next we look at the various characteristics of logic families. And the first characteristic that we are going to discuss is logic levels and voltage requirements of TTL and CMOS ICs. So we have seen discussed the classification of the logic families, and out of the all logic families, the important logic families are TTL and CMOS, transistor logic and complementary MOSFET family. So we'll look at the voltage requirements of the circuits that belong to these two families and so-called logic levels. So here something looks new, that what is meant by logic level. So here all the digital circuits are designed to input and output only two types of signals. That is, they will take only those two input signals, two types of signals, or they will output only those two types of signals. So then what are those signals? Those signals are called logic 1 signal, logic 0 signal. You know what is meant by logic 0 signal? So we are saying that a circuit is made up of some semiconductor devices and some circuit elements. Basically, it's an electrical circuit. For that, we should give either voltages or currents as inputs. We will get voltages and currents as outputs. But here, we are not giving a particular voltage as input, or we are not getting a particular voltage as output. But here, we are saying that the circuit is designed to input and output only two types of signals, or exactly they are called logic levels. So one is logic 0 and another is logic 1. So then what is meant by logic 1 and what is meant by logic 0? In a perfect world, logic 1 represents the full power supply voltage. That is, if you take supply voltage as 5 volts, then logic 1 represents 5 volts. And logic 0 represents the 0 voltage. So that is normally the voltages that we choose for logic 1 and logic 0 are 5 volts and 0 volts. So this is the case of ideal world where the voltage is, for example, if say if it is a logic 1 input or logic 1 output, say that the voltage is perfectly 5 volts, and if you say it is a logic 0, you say perfectly the voltage is 0 volt. However, this ideal case is not possible, as in real world there will be voltage drops when you connect the circuits using, when you connect digital logic circuits. So that means the 5 volt will not be exactly 5 volt and for to represent logic 1, and the 0 volt may not be at 0 volt perfectly for all the time to represent logic 0. So instead of choosing the exact levels the exact voltages to represent the logic 0 and the logic 1 levels, we'll use voltage ranges instead of exact voltages, and we'll choose a particular voltage level that represents logic 1 level, and we will choose certain voltage level which represents logic 0. So as long as the voltage that we are applying at the input of digital circuit falls within the range of logic 1, then it is treated as logic 1, and if it falls within the range of voltage range of logic 0, then it is treated as logic 0. So that means even though there are any voltage drops in the circuits, then since we are not choosing exact voltage level, since we are choosing voltage ranges to represent logic 0 and 1, the circuit will function normally as long as that particular voltage falls in the corresponding range. So that is why all the digital circuits will operate with are designed to operate to input or output logic levels, that is logic 0 and logic 1, where each of these logics levels has certain voltage range defined to be qualified as logic 0 or logic 1. So we look at the voltage requirements of the logic levels and voltage requirements of TTL and CMOS ICs. So here you can see in the diagram, right? So here the acceptable TTL gate input signal levels. You can see that the maximum voltage here we have chosen the supply voltage as 0 volts to 5 volts. In ideal case 5 volt represent logic 1 and 0 volt represent logic 0. But in practical case we define a voltage range that represents logic 0 at the input of circuit or input of a logic gate. So here for TTL it is defined as 0 volts to 0.8 volts. So any voltage which falls within this range, when that voltage is given as input for logic gate, it is treated as a low signal, or it is treated as a logic 0 signal. And similarly, we define the voltage range for the high signal or logic 1 signal, and the voltage range for TTL family, circuits of TTL family is for logic 1 is 2 volts to 5 volts. That means if you apply any voltage at the input of logic circuit which is anywhere between 2 volts to 5 volts, it is treated as a high voltage or logic 1 voltage by the circuit. So this is, I say that this is low level, this is high level. So this is called logic low or logic 0 level. This is called logic 1 level. So these are the logic levels at the input of the digital circuit for the circuits which belongs to TTL family. And you can see that similarly at the output of logic gate, the logic 0 is qualified by certain voltage range. That means if the output signal has voltage anywhere between 0 to 0.5 volt, then it is treated as a low signal at the output of logic gate. Similarly, if the voltage of the signal, the output of logic gate, output of TTL gate is anywhere between 2.7 volts to 5 volt, then it is treated as a high signal, logic 1 output. So you can observe that the voltage ranges for logic 0 and logic 1, the input and output are different. Are different. So at the input it is logic 0 is voltages are from 0 to 0.8, logic 1 voltages are 2 volts to 5 volt, and the output low signal has voltage range 0 to 0.5 volt, high signal has voltage range 2.7 to 5 volt. And if you observe here, there is a gap between the high level and low level. You can see if you apply voltage in the range 0.8 to 2 volt. You see that this neither qualifies as low signal or nor qualifies as high signal. So the digital logic circuits of TTL family should not be applied any voltage between 0.8 to 2 volt, because they are neither treated as high signal nor as low signal, and the operation of the circuit is unknown. So next we'll look at the logic levels and voltage requirements of CMOS logic gates, CMOS ICs. So here, similar to the TTL, we have taken, so for CMOS logic gates, the voltage requirement is 5 volts, which is the maximum voltage, and least voltage is 0 volt. And here you can see that the logic low level and high level have different voltage ranges compared to the TTL family. So here the low level corresponds to the voltage range from 0 to 1.5 volt. So you can see that this range is higher than the TTL gate. Similarly, the high level has voltage range 3.5 volt, 5 volt to 5 volt. That means any voltage which falls, which is less than 5 and greater than 3.5, if that voltage is applied at the input of a CMOS logic gate, then it is treated as a high signal by the logic gate. Similarly, so these are the ranges defined for the input signal. Similarly, the ranges are also defined for the output signal by the CMOS gate. And here you can see that for the output signal, the low signal has the voltage range of 0 to 0.5 volts, and the high signal has voltage range of 4.95 volts to 5 volt. So you can see that these voltage ranges are very narrow compared to the TTL gates of TTL family. So here you can see that, so we'll look at one of the diagram. So to define the general parameters of input and output, minimum and maximum voltages for each level, that is high level and low level. So by that we can define 4 levels. So first is high level input voltage. So high level input voltage, you can see that it's an input voltage. It's a high level input voltage. So what is that voltage? It's a minimum voltage level required for a logic 1 at an input. So you can see that the minimum voltage level required for a logic 1 at input is here 2 volts. So here in general I can say that this is high level input voltage VIH. Similarly, we can define the maximum voltage will be limited by the power supply, but the minimum voltage required for the signal to be qualified as logic 1 at the input is high level input voltage, that is VIH, and here it is 2 volt. Similarly, define one more voltage for low level at the input, which is the maximum voltage required for a logic 0 at input. So this is the maximum voltage that is required for a logic 0 at input, and this is called as low level input voltage. So this is VIL. Here VIL is 0.8 volt and VIH is 2 volt for this TTL family. So we define two voltage parameters here. So any voltage that is to be qualified as logic 1 at input should have voltage greater than VIH. Any voltage that is to be qualified as low signal should have voltage less than VIL. Similarly, we define two more voltages for the output signal. So here also same thing. So this is the any voltage, this this level we define, and this level we define in general. So first we define high level output voltage VOH. So it's a minimum voltage available for logic 1 at the output. So this is the minimum voltage for an output signal that is qualified as logic 1 or high signal. If the output signal goes below this, it is not qualified as a high signal. So to qualify an output of a TTL gate as a high signal, this is the minimum voltage and it is normally designated as VOH. Similarly, for an output signal of a TTL gate to be qualified as a low signal, the voltage must be, this is the maximum voltage. That means the voltage must be less than this level, and this level we call it as low level input voltage, that is VOL. So we have defined what is in the logical level and what are the voltage requirements of the two important logic families TTL and CMOS, and we define the various voltage levels which are used to decide whether input signal is a valid high signal or low signal, or whether an output signal is a valid high signal or valid low signal, and those voltage levels are the high level input voltage VIH, low level input voltage VIL, and high level output voltage VOH, and low level input voltage VOL. And here we have seen that all the digital circuits will are designed to operate or are designed to input or output only two types of signals, that is high signal and low signal, or logic 0 signal and logic 1 signal. and there is a specific range of voltages to be qualified as logic 0 or logic 1 at the input and output of logic gate, and these two are different. That is, at input it has different voltage range, and the output it has voltage range to be qualified as either high or low signal, and it is also different from one family to the other. And we have seen what are the voltage ranges that are required to be qualified as either low or high for both families TTL and CMOS. And for TTL, 0 to 0.8 volt will qualify as the voltage range for low signal. 2 to 5 volt is the range of high signal at the input. And for CMOS, 0 to 1.5 volt is voltage range for low signal, and 3.5 volt to 5 volt is the range for high signal. So next we look at few more parameters. So one more important parameter, that is called noise margin. So this unwanted electrical signal called noise signal can cause the voltages to rise or reduce from the intended value. That means the actual voltage may increase or decrease when this noise is added onto the signal, and this noise signal cause the circuit to malfunction when the voltages either decrease or increase from the intended value. The circuit, there may be a possibility of the circuit to malfunction. And for example, you can see that if so, these are the voltage levels for a signal to qualify as either high signal or low signal. So you can see that, for example, the signal input signal voltage is above 2 volt, just above 2 volts. So since it is above 2 volts, it will be treated as a high signal, and this is the case when there is noise. So for example, for the same voltage, if some noise is added and which is reducing this voltage below the 2 volts. So if it reduces the voltage below 2 volts, then what happens? You can see that, and after reducing the voltage below 2 volts, and this voltage will not be treated as high signal because it is out of the voltage range. So then the circuit will malfunction because the circuit is not treating the voltage as a high signal, and this is due to the added noise. So but the circuit has some sort of ability to tolerate the effect of noise, and what is that? And that limit of noise voltage that may appear at the input of a logic gate without any impairment or without any malfunctioning of the logic operation is called its noise margin. That means even though a noise is added to the input signal, but the limit of the noise level is such that it is within such limits that the added noise will not impact or will not impair the proper operation of the logic circuit. So then that level of noise or that limit of noise is called noise margin. So this how we decide how this noise limit of the noise voltage is provided is by choosing different voltage ranges for the signals at input and output levels. So here you can see that 2 to 5 volt signal will qualify as a high signal at the input, but a signal with lesser range 2.7 volt to 5 volt is qualified as a high output signal. That means when you connect two digital circuit, the output of the first circuit will be the input of second circuit. That means, so if a circuit has a high signal whose minimum voltage is 2.7 volt, then this signal will be treated as a high input signal even though its minimum voltage level is 2 volt. That means you can see that for this 2.7 signal, even though if a noise is added of minus zero point 0.7 volt, then it becomes 2 volts when it is taken as input by the second circuit. So even also it treats that noise added signal as a valid high signal, and since it is a valid high signal, it will not impair the proper logic operation. So here I can say that the noise margin is 0.7 volt, or I can say that if you take this as 2.7 and this 2, this is we generally define this voltage level as output high level voltage. And you can see from the previous slide with this is high level output voltage. So this is high level output voltage and this is high level input voltage, and you can see that at high level the noise margin is defined as VOH minus VIH. So the worst case high level noise margin is VOH minus VIH. Similarly, you can see at the input level the low signal has voltage range 0 to 0.8 volt. Similarly, the low signal for at the output of logic gate has range 0 to 0.5 volt. So we can see that when so the this output this output should have a minimum of 0.5 volt to be qualified as low signal, and when two circuits are connected, this low signal may be applied as input for the next circuit. But you can see that for the next circuit, to qualify as low signal, the minimum voltage, the maximum voltage must be 0.8 volt. So that means for the 0.5 volt, even if a zero point 0.3 volt of noise is added, that means it becomes 0.8 volt, even though it is treated as a valid voltage for low input signal. And since it is a valid signal, the circuit will operate without any impairment. So in general, you can see that instead of, since this is TTL, we are seeing the diagram of TTL, we have defined the exact voltages, but in general for any logic family, this voltage level, the output is VOL, that is VOL, low level input voltage. Low level output voltage, sorry, this is low level output voltage. And here you can see this low level input voltage. And you can see that the amount of the limit of noise tolerated at the low level is VIL minus VOL. So the worst case low level noise margin at the limit of noise that can be tolerated by the circuit is VIL minus VOL. So here the noise immunity or noise margin of a digital circuit gives the amount of noise that can be tolerated by the digital circuit, and here the amount of noise that can be tolerated is different for high level, different for low level. So by that we have two types of noise margins, low level noise margin and high level noise margin. The low level noise margin in general defined as VIL minus VOL, and this difference of voltage can be added to the low signal, but still it will operate without any impairment. And similarly, we define high level noise margin as VOH minus VIH. So still this much noise may be added for high signal, and still it will be treated as a valid high signal. So this is very important characteristics noise margin for digital circuit, which is very useful when you want to make a logic circuit and to know that what is the maximum noise that can be tolerated by that occurs actually, and based on the maximum amount of noise that occurs naturally, you design your circuit such that under the worst case also your circuit will function normally. And we'll discuss few more characteristics in the coming class. Thank you.